Okay, so we're going to go through an example of reducing and analyzing a circuit here. So find the equivalent resistance of this network here, this circuit, and the current in each resistor. So we have an EMF, a voltage of 18 volts here, and we know the amount of resistance of each resistor. And so the first step is to reduce this circuit down to one total equivalent resistor. And we do it step by step, right? Because we have this guy in parallel with this guy, and then that combination is in series with this guy. And so that kind of outlines our process. So I'm going to go ahead and draw each step here. So we can do a equivalent resistance where we still have that 4 ohm, but we have it connected to some equivalent resistance which we've yet to find. So R equivalent. I'll label it 1 since there will be more, right? All right. So to do this, to combine the 6 ohm in parallel with the 3 ohm, we apply the equation 1 over R equivalent. I'll do 1 is equal to 1 over R1 plus 1 over R2, and that's all we have. So that is 1 over, I'll do the 6 ohm first, plus 1 over 3 ohm, right? And so that, if you figure that, is equal to 2. Oops, I wrote an ohm. 2 ohms. So our equivalent resistor for that combination is 2 ohms. So I'm just going to go ahead and write 2 ohms here. 2 ohms. But we're not done yet because we still have a couple resistors and we need to know how they add. So we want to find, ultimately, if there's just one big resistor that is equivalent to both of those combined, right? Are equivalent to. So these two are in series with each other. And so we add them according to series. So R equivalent 2 is equal to R1 plus R2, which is equal to 4 ohms plus 2 ohms, which is 6 ohms. And so this resistor over here, this equivalent resistor, is a 6 ohm resistor. All right, and we still have our 18 volts of potential difference applied to this circuit. And so we can find the current through this would-be equivalent resistor here, right? Given that there is a potential difference across it of 18 volts, because it's the only thing on the circuit now. And so the current is found with Ohm's law. So down here, V equals IR, right? And so if we solve for the current, we have I equals V over R. And so we have 18 divided by 6, right? 18 volts divided by 6 ohms, which is 3 amps. And so the current through it is 3 amps up there. All right. And because we know that current is equal through all things in series, if we work backwards now, I'm going to do a new color. If we work backwards now over to this one, or here like this, then current is still going to be 3 amps. I guess I should be writing it with this one, right? Current is still equal to 3 amps for each of them. It's also, oops, it'd be the other way. It's going this way, 3 amps. And for that matter, if you were to analyze what the current is right there, it's also 3 amps. And the current right here, that's also 3 amps. right? Current is equal through all things in series. This entire circuit is one big series segment. So the whole thing has current of 3 amps if this middle one is our circuit. So now let's graduate over, work our way back to our original circuit and see what we have. Actually, before we do that, let's figure the potential difference. So 18 volts was the potential difference for that one on the right. So there's a potential drop across each of these associated with how much current and resistance is involved, right? So same thing, Ohm's law down here. So let's do this one. Ohm's law says V equals IR, yeah? And we want to find V across that individual circuit element, which has 3 amps of current going through it, and it provides 4 ohms of resistance to the circuit. So that's 3 amps times 4 ohms. So that's 12 volts of potential difference, right? So I'm going to go ahead and write that there in red, 12 volts, right? So remember, volts is just like this potential difference from high to low, and so for that circuit element, that's the potential drop there, right? Starts off really high at the top of the hill at the start, the positive terminal of this EMF source, and as it goes through certain circuit elements, right? So if this is the positive terminal of the EMF, right? Positive EMF, I guess, EMF. Then it travels, does nothing as it goes through the wire, and then it hits that 4 ohm resistor and it drops. And this drop is associated with 12 volts. And then it keeps going and it drops some other amount across that 2 ohm resistor, and we're about to figure out how much it drops. So for the 2 ohm resistor, same deal, same amount of current going through it, but its resistance is 2 ohms. And so you would have a 6 volt drop, so half as much. So let me draw that a little bit better, something like this. So this would be like for your 4 ohm resistor, this is for your 2 ohm resistor, and then it makes its way, no potential drop, all the way on the, on this part of that circuit, and then it hits the EMF, which brings it back up. I guess I'll connect it. Brings it back up to there, and it brings it back uphill, right? Or if this is time on the x-axis, and it brings it back up to that same elevation and then starts the journey again, right? And it continues and continues. All right, so this is 6 volts. Now we back out to the other one, and nothing's changed here. We know that the 4 ohm resistor has 12 volts going, 12 volt drop, and it has 3 amps going through it. But now we know that this potential drop is 6 volts, but what are the amps? What is the current through each of these, right? Each of these paths has its own individual associated current. The voltage is the same from point B to point C, but there's different amount of current depending on the magnitude of resistance on each of those lines. So we figure that out again with Ohm's law. So if we have V equals IR, and we're solving for the current, so we want I is equal to V over R, and the voltage is 6 volts, right? 6 volts across, regardless of which path we're talking about. And I'll start with the top path. The resistance on that top path is 6 ohms. And so if you do that, you get 1 amp. And so on this path up here, through resistor, this 6 ohm resistor, on this circuit, there is 1 amp of current going through it. Now let's do the bottom one. Bottom one, same process. So we have I being equal to V over R, which is equal to the same 6 volts voltage is equal across all things in parallel. That's that concept that, it has to go down the same elevation change in order to meet back up with the circuit and continue on. So voltage is equal, still 6 volts, but now we have a different amount of resistance on this lower path here, right? And so we have 3 ohms of resistance. And so that would translate to 2 amps. And so through the bottom line there's 2 amps of current going through resistor, that 3 ohm resistor in the original circuit. And there we have it. We have found the voltage drop across each component, and we've found the current through each component of this circuit by breaking it down, simplifying it to just one single element, one single resistor that's equivalent to that whole combination of arrangement, and then building it back up after we found the current using just our bits of logic of current is equal through all things in series, voltage is equal through all things across things in parallel, and using Ohm's law, which is, as I had said before, a big deal. You're going to use it a lot, as you already just saw. All right, next we talk about Kirchhoff's laws.